This is the chapter 12 homework. We know that this is a really complicated chapter, and even though the homework here, I tried to assign a reasonable number of problems, it doesn't encompass everything. So we're going to need to make sure we do some practice at the end of this semester and next semester to make sure that you've got a good shot at getting correct answers when they give you a free response on the topics. Especially, I think you need to do a little more with angular momentum, but we can talk about that at some point. So problem 13 has basically 4 point sources at different corners of a rectangle. It's a rectangle, not a square, because notice 10 centimeters width, 8 centimeters height. So it's asking you to find the center of mass. So in the x-plane, that's this plane, we take the mass of these two things and multiply it by that distance, and then divide it by the mass of the total system. So that gives us a center of mass of 5.71 centimeters to the right of the origin. And the origin is at point A. The center of mass for y is up. So again, 200 grams times 8 centimeters plus 200 grams times 8 centimeters. But you divide by the total mass of the system and you get 4.57 centimeters. So the center of mass would be somewhere around here, but that is actually going to be to the right 5.71 centimeters and up 4.57 centimeters. So for part B, it's asking, that's fantastic. It's asking about the moment of inertia if it's rotated about this point. So imagine something spearing point A and then all the rest of it was rotated through that. That means that point B is going to be 8 centimeters away from A, point D is going to be 10 centimeters away from A, and point C is going to be some other distance, which I figure out with the Pythagorean theorem, so it's 12.8 centimeters away. So essentially, since these are point sources and they're rotating about this axis, we're going to treat them as a bunch of individual point sources. So each one is its own mr squared. So to put it in standard units, point B is 0.2 kilograms at 8 centimeters away, so that's 0.08 squared. Point D is 0.2 kilograms at 10 centimeters away, so that's 0.10 squared. And point C is 200 grams or 0.2 kilograms at 12.8 or 0.128 meters away. And then we square that. And so that's the total moment of inertia for that whole system if rotated about this axis. If you rotate it about different axes, that might change because this is not the same mass as the other masses. So it actually would change. P18 was simple. So if you have a 30 Newton force pulling this way and a 20 Newton force pulling that way, 4 centimeters radius, so 0.02 meter, or 0.4 centimeter diameter, so 0.02 meter radius, 30 newtons times 0.02 meters gives me 0.6 newton meters of clockwise torque, 0.4 newton meters then of counterclockwise torque. So the net torque is 0.2 newton meters, and that would be clockwise. Or recognizing that clockwise torques are negative, it would be negative 0.2 newton meters. For problem 24, I really like this because it gets to the idea of something that we know pretty well linearly, but you may not be familiar with angularly. So here's a torque versus time graph. Well, you should be familiar with the fact that a force versus time graph is equal to impulse. So a torque versus time graph would equal angular impulse, which is weird. I don't even know the symbol for it. At any rate, we know that the moment of inertia of the system is 0.4 kilogram meters squared. So the angular impulse is the area of this graph, torque versus time. So when I multiply those together, which is a triangle, I get 2 Newton meters seconds, which are kind of weird units. But then again, Newton seconds are also kind of weird units. So if the linear formula for impulse momentum is Ft equals m delta v, then for angular systems it would be torque times time equals moment of inertia times delta omega. So again, that's the change in angular momentum. So in this particular case, I get that the torque times time, which is the area of the graph, is 2 Newton meter seconds. We're given that this is 4 kilogram meters squared, so the angular momentum would be 0.5 radians per second. The other way you could do this is in purple here. So the average angular acceleration would equal the average torque divided by the moment of inertia. Well, this goes from 0 to 2 newton meters of torque, so the average would be 1 over that whole time. That would actually give you the same area of the graph, by the way. So 1 newton meter torque divided by 0.4 or by 4 kilogram meters squared of inertia will give me an angular acceleration of 0.25 radians per second squared. And therefore, that times time would give me my final angular velocity. So 0.25 times, that should be actually 4 seconds. Nope, 2 seconds. I'm an idiot. It says 2 seconds right there. So that's 0.5 radians per second, which is the same final angular velocity. Problem number 31 is a torque problem. So you have a cat over here, a cat here, some cat food at the end. It's kind of weird. This is similar to an example we did in class. So you're given the mass of this, you each know the distance from the fulcrum. The question is, how far can this cat walk out before something tips over? That's kind of a stupid problem because it would tip over the other way if it was anywhere else. But I get what they're trying to do. And so when you solve that with torque counterclockwise equals torque clockwise, you get that this distance d is 1.5 meters. So you should probably clarify and say that that is 1.5 meters to the left of the fulcrum. Key aspect to remember is things are always measured from where you choose the fulcrum when doing torque problems. For P32, you have an object here. You're given the diameter, so we have to get the radius. You're given a speed. You're asked to convert that to angular speed. Well, when I do that, I get 66.7 radians per second. It asks for revolutions per minute, or RPM. So I did the conversion there. 1 revolution is the same as 2 pi radians. 60 seconds is the same as 1 minute. Notice I showed my units when I did the conversion because I want to make sure I don't screw it up. So I think that's important. So that ends up with revolutions on top, minutes on the bottom. Everything else cancels out, radians and seconds. So fun thing about this is, if you remember back, I think it's from chapter 4, or whenever we looked at rotating things, might have been chapter 8, the speed at the top point of the wheel linearly is going to be double the average. So this average speed of this is what the center of mass is moving. The top part of the wheel is moving forward relative to the center of mass, so it would be going twice as fast. That's 40 meters per second. The bottom part of the wheel, at the instant it touches the ground, isn't moving at all. It is planted at that part. That's why when we think about friction of a wheel, if you slam on your brakes, it would be static friction, not sliding friction. So that is going 0 meters per second. P45, you have a rod. It's a total length of 2 meters. It's going 120 RPMs, or revolutions per minute. They're asking for the angular momentum of that. So the first thing I want to do is convert this into angular speed. So 120 RPM, and that's 2 revolutions per second, and then times, because there's 60 seconds in a minute, times 2 pi radians over 1 revolution gives me that angular speed. So the moment of inertia is times the angular speed is equal to the angular momentum. So for a rod, a uniform rod, meaning the same density everywhere, I've got 1/12 ml squared. Notice L is the entire length, not the radius. If you wanted to think about it as the radius, it would be obviously a different coefficient in front. So a significantly different coefficient, because L here is 2 meters, so 2 squared is 4. The radius would be 1. So this would be like a tiny fraction in front of that. So 1/12 ml squared. So that ends up being 0.167 kilogram meters squared. So then multiplying that moment of inertia by the angular velocity gives us the angular momentum, kilogram meters squared per second. So just keep an eye on your units. Sometimes the AP really is a stickler on the units in your final answers, and they certainly are on graphs when they ask you to put units on graphs. At some point, the AP actually did do a problem where they gave you that the moment of inertia of a rod rotated about its center axis is 1/3 ml squared, and then they asked you to figure out the formula for the rod rotated about its end. And so basically it was a proof of knowing that about the center it would be 1/12 ml squared, and then you use the parallel axis theorem, which is md squared, to figure out the total moment of inertia. And so that distance is L over 2. It basically comes out to, if you rotate it as a point about this end or this end, it would be 1/3 ml squared. 62 is a problem similar to one which I had on my notes, but I don't think I got to in class. So hopefully you looked at that. This is very colorful, by the way. So there's a beam, the person's hanging out here eating lunch for whatever reason, and the goal is to find out, is this a safe situation? So what you should recognize is the cable is going to have tension because it's holding up the beam. The beam center of mass acts here. As the person gets farther and farther from the wall, they're going to create more torque that would be clockwise, and therefore the rope is going to have to pull with more tension to oppose that. So things to remember: clockwise torque equals counterclockwise torque, downward force equals upward force. For me, I'm choosing this pivot point or my fulcrum as the wall because the wall is definitely interacting with the beam, but I don't know exactly how. I know there's going to be a force. I don't know whether it's up, down, left, right, some components of both. So that way I eliminate that unknown, and therefore my only unknown is the tension in that particular cable. So T for tension. Anyhow, in this particular case, when I put the fulcrum there, the counterclockwise torque is caused by this tension. It's at a 30-degree angle from the perpendicular. So I said F cable 6 meters away, sine of 30 degrees gives me the vertical component. The clockwise torque is going to be caused by the weight of the person plus the weight of the beam. So that's 80 times 9.8 times 4 meters away, because that person is 2 meters from the right end, 4 meters from the fulcrum, plus 1450, 9.8, 3 meters away, because the beam center of mass acts 3 meters away from the wall. So when I do that, I get that the force in the cable is around 15,255 newtons. Even rounding that off, that's definitely unsafe because the cable was only rated for 15,000 newtons. So big idea, you're using torques to find the force in the cable. The weight of the beam acts at its center of mass. The last couple problems here are pretty challenging. I would encourage you to go and look through 69 on my PDF. I've got 3 different methods here for solving this. Maybe there's more. Big idea here, we're trying to find the time for this to get to the ground. I know I did do a problem like this in class. So there's the first method I thought of is think of everything as linear measurements. So think of it as a force problem. So if this is 4 kilogram block, 2 kilogram block, the pulley was 2 kilograms, the radius was 0.06 meters. It said friction caused a torque of 0.5 newton meters. So that's a little bit of a wrench to throw in there. So what I have to do here, if I want to do F net over equivalent mass, I get the net torque. So that's really caused by the difference in masses here. So those are listed. But I also have to take off the force due to friction. So that's a little bit tougher. To find the force of friction, I've done that in blacking down here. We could think of it as force multiplied by a distance would equal the torque. Well, the torque was given at 0.5 newton meters. So if we thought of that as friction acting at the edge, it may not act at the edge, but let's think of it as if it is, because we have these gravitational forces acting at the edge. Then that's an equivalent force of 8.33 newtons, and that would oppose whatever direction the pulley is turning. So plugging that into this general formula here, we got 39.2 minus 19.6 minus 8.33. The equivalent mass is 7 kilograms because 4 plus 2, and I don't know why I did that like that. I'm going to make that bigger again. 4 times 2, and then half the mass of the pulley since it said it was a solid disk. So when I get that, I get 1.61 meters per second squared, and then I plug that into this general kinematics equation, get the time to fall as 1.1 seconds. Method 2 I could think of with torques. So I could convert those forces to net torques. In some ways I think this is a little easier. So the forces on the edge create a net torque of 9.8 times 4 times the radius there. That's my clockwise torque. My counterclockwise torque. My clockwise torque is caused by the other mass and friction. So the net torque is 0.676 newton meters. That divided by the radius would give me the force, since the forces or torque is equal to perpendicular force times the distance. So that's 11.3 newtons. Gives me the same thing I had up here, by the way, 11.3 newtons, and then divide it by the equivalent mass. Third one is not using the equivalent mass formula. The third one is using moment of inertia, and moment of inertia and then net torque to figure out the angular acceleration. The angular acceleration, then I can convert to linear acceleration and do the same thing. Okay. So for problem number 74, which is the last one, we've got an axle and it's on the very edge of a solid disk. So this is going to be a parallel axis theorem problem. So in this particular case, we've got the diameter, it said it was 60 meters. That's annoying. So the radius is 0.3 meters, or 60 centimeters. So the radius is 0.3 meters. Mass of this thing is 5 kilograms. So if this center of mass is directly sideways from that axle, which is a little weird, it's going to create a gravitational torque, which was also talked about in the problem, or in the book. So the initial angular acceleration is going to be caused by this torque. So I basically have to go back to Newton's second law for rotation. Alpha equals net torque over moment of inertia, which is the equivalent of F net over m tot. That's how I get the net torque. The total moment of inertia is equal to that of the disk plus the extra because it's not being rotated about the center. So that's your parallel axis theorem. So there's the net torque. The disk is 0.5 mr squared. The extra is md squared. So d is the distance of the center of mass to the axle. So we treat that center of mass as a point source when thinking about the parallel axis theorem because we've already taken how the shape affects the moment of inertia into account here. So adding those two things, my total moment of inertia is 0.675. My torque was 14.7 newton meters. I get this acceleration. The last part is tricky. This whole stuff is tricky, I guess. So we would need to think of it as an energy problem. So when this thing falls down, it's going to end up moving, but it's only going to move rotationally. So I thought this was tricky because when you think about the rolling races of things on a hill, we usually have gravitational potential energy go into both linear kinetic energy and rotational kinetic energy. But at the bottom, it's only rotational kinetic energy. So that's why I use this version of the formula, solving for the final angular velocity down here. That's not hard to do once you realize that's what you do. So I think, again, that's a little bit tricky for sure. Note that the reason part A asks for the initial angular acceleration is that here, as this center of mass gets lower and lower, the torque will get lower and lower, even though the moment of inertia would stay the same. So your angular acceleration is definitely not constant. At the bottom down here, there is no angular acceleration at all. Once the center mass is directly below the axis. So that's a lot of information on this. Like I said, pretty challenging topic, and we'll go over a few of those in class.